Hey everybody, here we are at 9.5 notes. We're still trying to work on divergence and convergence of series. Today we're going to look at something called alternating series and determine whether they converge or diverge. And then we can estimate the value of an alternating series to approximate the sum, but we can't get the exact sum. And then we're going to also look at absolutely or conditionally convergent series, and we're not going to do this, so we can cross that out. Okay, so alternating series have positive and negative terms. A lot of the tests we've done so far, all the terms had to be positive. So alternating series is one where they switch back and forth. And so here's just an example. We're just going to write the first 5 terms. If we plug in 0, we get 1. If we plug in 1, we get negative 1/2. If we plug in 2, we get 1/4. Plug in 3, we're going to get negative 1/8. And if we plug in 4, we're going to get 1/16. So you can see how they go from positive to negative to positive to negative to positive to negative. And another way we could have written this is using that negative 1 to some power, right? And negative 1 to the n power times 1/2 to the n, right? So it's kind of removing or factoring out that piece that makes it negative. And then what remains, the thing that remains here, can be analyzed kind of separately of, the piece that makes it negative. And in this case, that piece that's not this separate piece over here is a geometric sequence. And so, we could talk about convergence if it wasn't negative there. All right, so there's this thing called the alternating series tests. And so what's required here is for you to actually be able to separate the negative piece, right? That thing that makes it negative, just as a, kind of like if you want the first term to be negative, then you write it like this, right? This will make the first term negative. Because if you plug in a 1, you're going to get a negative here, right? And then this here, what this does, this one makes first term positive. Because if you plug in a 1, you're going to get negative 1 to the second power, which makes it positive, right? And then what you have here is just the formula for your nth term, right? And so we can look at, if we can write it this way, then we can look at that formula for the nth term kind of separately, and it will help us determine the convergence of the alternating series. So here's how we know if it converges, right? So first of all, the limit of that nth term as n goes to infinity must be 0, right? That's that same condition that we've kind of been doing our test for divergence. If the limit is not 0, then it diverges, right? And then if this is basically the next term is greater than the now term for all n, then it will converge, right? With the n plus 1 means we're on the next term, right? So every successive term is less than the one before it is what it's saying, right? If we keep going, the terms will be decreasing. I guess another way to say this is that terms are decreasing, right? Because the next term is always smaller than what you currently have. All right, so there's only 2 conditions here, right? Then if you can show those 2 things, then you can show that it is convergent. All right, so let's look at our first example here. We have this, the sum from 1 to infinity of n divided by negative 2 to the n minus 1. And the first thing I want to do here is kind of get rid of that negative piece, that piece that's making it positive, negative, put that on the outside. So you can see that it's coming from down here because it's negative 2 to the n minus 1, right? That negative 2 will, you change the sign of it each time. So we're going to go ahead and rewrite this as, we're going to take that negative piece to the outside. We have to decide, should I be using n or n plus 1 or something else up there? You could just use n minus 1 on this guy, it would work. The idea is, do I want my first term to be positive or negative? So let's just check. If I plug in 1 to the original thing here, I should get 1 divided by negative 2 to the 0 power. which would be positive 1. So I want this first piece to be positive, which means when I plug in 1, I need to get a even. So I'm going to go ahead and put that up there. Again, you could have put n minus 1. It would work too. And then this will be times whatever's left over here, which we can now remove the negative piece there, because that's taken care of with this. Right, so this is our an, right? This whole thing is our an, and the thing that changes the sign is this piece. And so we need to check two things. Does the limit of an equal 0? So let's check that first, right? First condition, does limit as n go to infinity of n over 2 to the n minus 1, does that equal 0? Well, the top piece is linear, the bottom piece is exponential. Exponentials always grow faster, right? So this is going to be kind of like small over big, which is going to go to 0, right? Exponentials grow much faster than linear. And then we also need to check that the terms are basically decreasing, right? An plus 1 is always less than an. So what we're trying to show is that let's do an first, right? This is an, this is the nth term. What does an plus 1 look like? Well, what that looks like is just everywhere you see an n here, you're going to put n plus 1, right? So instead we're going to write n plus 1 divided by 2 to the n plus 1, and then there's that minus 1 that was there already. Right? So you can clean that up and say, okay, well, n plus 1 minus 1, those just go away, right? That's just 0. So it's just that. Is n plus 1 divided by 2 to the n, is that less than or equal to n divided by 2 to the n minus 1? Well, this should be kind of obvious, right? Like, because these denominators are growing faster, 2 to the n will be greater than 2 to the n minus 1, and so you'll be dividing by a bigger number, which will make it less than. But let's just show some terms, right? So let's just do, like, n equals 1. If I plug in 1, we get 2 over 2, right, which is 2 here. If I plug in 1 on this one, we get 1 over 0, we get 1. Sorry, 2 over 2 is 1 here also. We both get 1. If I plug in 2, I get 3 over 4 here. And this one we get, plug in 2, you get 2 over 2, which is 1. And then plug in here, plug in 3, and you're going to get 4 over 8, which is 1/2. 4 over 8. And if I plug in 3 here, we're going to get 3 over 4. And what you should notice is, because we're just doing the next term, you should see this relationship where, it's just, the next one here is just going to be this one. So what you can see, though, is all these ones are always smaller than those ones, except for in the first one. That's why there's that or equal to bar. And so both conditions are met here, so it will converge. We don't know to what yet, but we know that it converges. Next one is already written in that form for us, right? They separated the negative piece for us, and this is our nth term. So we just need to check two things. Does the limit as n go to infinity equal 0? Right? Does that equal 0? Yes, it's 1 divided by infinity. It goes to 0. Next piece 2, we need to compare our two things. So we're going to write, here's an, which is 1 over n, and then an plus 1 is simply replace your n with n plus 1, so it's going to be 1 over n plus 1. So the question is, 1 over n plus 1 less than 1 over n? Is it always less than? And these are always for n greater than 1, greater than or equal to 1, right? So just imagine I do 1 divided by a number plus 1. Is that always smaller than 1 divided by that number? The answer is yes, right? This piece will always be bigger than that piece because you're adding 1 to this, and then you're dividing by that. So yes, this will be true. So we can say that it converges. All right, so next piece, or next problem. Again, there's that piece that makes it negative. and our an is this, right? That's our an. So we want to check limit as n goes to infinity of this. And what we notice here is that this is going to go to 1, which this means that it diverges, right? It's the same thing as our nth term test for divergence, right? If that goes to 1, then it diverges. So in this case, the alternating series, test just says that it diverges. This alternating series remainder will give us an estimate of what our series converges to. So Sn, remember, is our partial sum. So for a convergent alternating series, the partial sum can be a useful approximation for the sum S of the series. The error involved using the partial sum, right? This is the real sum. The real sum is approximately the partial sum. It can be determined by the remainder, which is taking the real sum minus the partial sum, and then that will help give us an estimate. So let's see how this works. So what this says is that the remainder, which is basically the remainder is defined by taking the real sum minus the partial sums. The remainder is always less than the n plus 1 term, right? So basically, if you can find this term, then you'll have a estimate on like how far away you are from the actual sum. So this is easier done with like an example, right? So here's our first example, and we want to approximate the sum of the alternating series. So let's go ahead and write out this one real quick. This is going to be 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial minus 1 over 6 factorial, right? And it keeps going like that forever, alternating between positive, negative, positive, negative. We can check that this series converges, right? If we take the limit as n goes to infinity of 1 over n factorial, that's 1 over infinity, which is 0. And then we can also show that 1 over n plus 1 factorial, right? That's the an plus 1 term, is always less than 1 over n factorial, right? Like, because again, you're dividing by a slightly larger number. This will always be true. And so this series converges. So how can we estimate what it converges to? Well, what we can do is we can find S sub n, which S, let's estimate using the first 6 terms in this case, and the instructions would tell you how many terms to use. So S sub 6 is the partial sum of the first 6 terms, right? Which means we just add up these first 6 terms, right? So you get a calculator and you do this and you add up, 1 plus 1 minus 1/2 plus 1/3. You add them all up, right? And if you do that, please do it. What you're going to get is 91 over 144, which is approximately 0.63194, right? You can just do that on a calculator. And so what the alternating series test remainder thing says is that the remainder, if I took the actual sum and subtracted this partial sum, we would get, this is equal to the remainder of the first 6 terms, which will always be less than or equal to the 7th term, right? Which the 7th term is 1 over 5040, right? The 7th term is 1 over 7 factorial, which is 5040. So what this says is that the sum of this series lies somewhere between this number plus or minus this number, which this number is about this is about 0.0002, meaning the sum, the real sum, let's call it big S like usual, has to be greater than this minus excuse me. So it has to be greater than the partial sum you found minus this seventh term, and it has to be less than the partial sum you found plus the seventh term. This kind of makes sense because you're going to add or subtract the seventh term and then add or subtract the eighth term, which will be smaller than that, and so on and so forth. And so our actual sum has to be somewhere in between that. And so you have a really good estimate of what your sum should actually be, right? All right, let's try another one. Excuse me, let me pause this real quick. Okay, so here's the next one. Again, let's go ahead and just list the first few terms here. If we plug in 0, we're going to get 1 over 1, right? We're going to plug in, we're going to get 1. If we plug in 1, we're going to get negative 1 divided by 2. So negative 1/2. If we plug in 2, we're going to get positive 1 over 4 times 2, which is 8. And for this one, let's use the, it doesn't specify here, but let's say it says use the first 4 terms. We'll just make our life a little bit easier to create an approximation, right? So we just need one more. If we plug in 3, we're going to get a negative 1 divided by 8 times 3 times 2, 8 times 6, which is negative 1 over 48, right? Let me go to erase this so it's not in our way. So we need to check for convergence, right? So again, we're just going to check is, we're 1 over 2 to the n times n factorial. That will converge to 0 as n goes to infinity. And then is each successive term smaller than the last? Yes, you can kind of see that here, right? They are decreasing. They're getting smaller and smaller. And so what we're going to say is that the remainder, our 4, right, is less than A5, right? So let's get that fifth term. We're not going to use it for our sum, but we need the fifth term to calculate the remainder. So plug in 5, we're going to get, sorry, we're plugging 4 because that's the fifth term. Plug in 4, you're going to get a positive 1 over 2 to the 4th power, which is 16, times 4 factorial, which is 4 times 3 times 2 times 1. So 16 times 4 times 3 times 2, which is going to give us 384. So in this case, we have 1 over 384. So what it's saying is the remainder has to be less than 1 divided by 384, which is about 0.0026, which means our actual sum is, here, let's do this first. Our S4, our partial sum here, is adding up 1 minus 1/2 plus our first 4 terms, right? So let's do this. 1 minus 1/2 plus 1/8 minus 1/48. This is our fourth partial sum, which is 0.604. So our actual sum, which is going to be S, must be our fourth partial sum. It must be greater than our fourth partial sum, which is not that, minus our remainder, which is 0.0026, and it must be greater than our fourth partial sum, plus our remainder, which is plus 0.0026, right? And so this will give us a good estimate of what our real sum is, right? It gives us error bounds, right? And you could actually calculate this, do 0.604, right? 0.604 minus 0.0026 is 0.6014, and then we can do 0.604 plus 0.0026, and this will give us 6.066, right? So we know that the S must be between those two numbers there. That the actual sum is between those two numbers. And you can see how we could get a better and better estimate by just using more and more terms. All right, so that's the alternating series test and how to get the remainder piece there. Next thing we're going to talk about is absolute versus conditional convergence. To do this, let's look at this series real quick and see how it's kind of like a weird one, right? So for this, we're going to go ahead and just, let's look at some of the terms. This would be sine 1 over 1 squared plus sine 2 over 2 squared plus sine 3 over 3 squared plus sine 4 over 4 squared, and so on and so forth, right? And if we want to see what these actual numbers are, you do sine 1 over 1, which is going to be, 0.841, and then if we do sine 2 divided by 2, divided by 4, sine 2 divided by 4 would give us 0.227, and sine 3 divided by 9 would give us 0.0156. And here's the interesting one, I believe, sine 4 divided by 16 is, oh no, this is why this one's weird. You get a negative there, right? Which is like, oh shoot, this is not an alternating series. It's not going positive, negative, but this is going to be negative. And if you recognize that sine, sine is going to be negative for a little while, and then, once it'll come back around and be positive again, and it'll alternate between positive and negative, but not like an alternating series, right? It's not going to just bounce back and forth every single time. And so we can't use the alternating series test on it. What we could do is we could use that thing we kind of talked about in the beginning, which is take the absolute value of the nth term, right, of that formula, and then we could compare this using the direct comparison test. We want to compare it to something similar. So we could compare sine n over n squared to 1 over n squared. And you want to know, well, which one is greater, right? And so in order to figure this out, you have to know that sine n is always less than 1, right? Because you can't get any numbers bigger than 1 out of sine n, or absolute value of sine n, right? Because it's always going to be less than 1. And so you have to think about which one's bigger, 1 divided by a number or a number less than 1 divided by a number. And hopefully you can see that a number less than 1 divided by the same number is always going to be less than. And so we can show that the absolute value of sine n over n squared is always less than 1 over n squared, and 1 over n squared is a p-series, right? This is a p-series with p equal to 2, and that p-series converges, and this one's less than that one, so this one also must converge by the direct comparison test. We'll put that. I don't really think on the AP exam you're allowed to do that, but I don't want to write it out. Right, so this kind of leads us into this thing about what we're going to call absolute convergence. It has to do with absolute value. We say that if the absolute value of a function converges, then the series also converges. So we say that a series is absolutely convergent if the absolute value of that series converges. But there are these series in which the series itself converges, but the absolute value of the series diverges, right? So if that's the case, then we call it conditionally convergent, right? So if the absolute value does not converge or diverges, but the original does converge, then it's conditional. But if the absolute value converges, then it's absolutely convergent. All right, so let's do a few examples so you can see how this goes. So this is going to require some of our old tests as well, right? Okay, first one. We are sorry, give me a second. Okay, so the thought process here is one, if the original series diverges, then so will the absolute value, right? Because the absolute value will always be bigger than the original. So if you can just show that the original series diverges, then the whole thing diverges, right? Now, if looking at that original thing is challenging, like it's not alternating or whatever, then you want to look at the absolute value. And if the absolute value of the series converges, then we say it's absolutely convergent. And then there's this case where the absolute value diverges, but the original does not. Okay, so like the first thing we want to check is just, does this original thing, can I just check that the original thing diverges, right? So let's just do the first thing we should always be doing, or let's just do our nth term test for divergence. This is an alternating series, so we're just going to look at that, n factorial over 2 to the n. And I don't know if you know by now, but factorials are one of the only things that grow faster than exponentials, so this is going to be big over small. Which all that's important here is this does not equal 0, so this means that this series diverges, right? And if a to the n diverges, then so does absolute value of a to the n, right? So like the whole thing just diverges, we don't have to worry about it anymore. It's done, right? So that's it. Next one is this. This is an alternating series. If you notice, it's just like if it ever has that piece that's making it positive, negative, it's alternating series. So we can just check using alternating series test, which is first check the limit as n goes to infinity. If we do that, it's going to be 0, right? 1 over square root of n goes to 0. And then 2, we need to show that every next term is smaller than the last. So we need to show that this will always be smaller or equal to this, which it is, right? 1 divided by a number plus 1 is always smaller than 1 divided by that number. So that works. So this converges, right? However, we want to say if it's conditional convergence or absolute convergence. So let's test the absolute value to see if that converges, right? Well, what does the absolute value do? It gets rid of that negative piece, right? So we're trying to check, does 1 over square root of n converge? And, first check for divergence, like the limit as n goes to infinity. We kind of already did that. It goes to 0, so that doesn't help us. Maybe you can recognize this as a p series, which is 1 over n to the 1/2, where p is 1/2. So does it converge or diverge? Well, p is less than 1, which means it diverges, right? Since your power is less than 1, this diverges, which means the absolute value piece diverged, but the original converged. So we would say this is conditionally convergent because the absolute value does not converge, but the original does. All right. So next example here is this funky looking thing. Notice how, like, please notice how this piece here is just gonna, you know, change the sign of it. However, it's not like as straightforward as the other one. We could write the first few terms here if we wanted to, just to see how it goes. We would get negative 1/3 minus 1/9 plus 1 over 27 plus 1 over 81 minus whatever. Notice how like they all are changing signs, but it's not alternating back and forth. So it's not an alternating series. So, you know, maybe we're not really sure how to go about it. So what we can do is just go directly to our absolute value test, right? So if we take the absolute value of this, that messy thing, what's going to happen? Well, all the negative piece goes away, right? This chunk is just going to go away, and we're going to be left with the 1/3 to the n. You don't need the absolute value bars anymore because that can never be negative. So we have 1/3 to the n, which is the same as 1/3 to the n. Do you recognize what that is? Hopefully you do. This is a geometric series. It's a geometric series with r equal to 1/3, which means it converges, right? Because the other r is less than 1. Now don't get too ahead of yourself saying, oh well, it converges to, and use that formula for the you know, you don't think you can use that to determine the value of this one, because remember, this one's adding some and subtracting some, right? So you could use this to find the value of the absolute value, but not that. But really what's important here is the absolute value, the sum of the absolute value converged, which means it's absolutely convergent. It converges absolutely, and the original must also converge. Right, this is kind of like the direct comparison test. Like if you can show that the bigger one converges, then the little one must converge, right? And the absolute value must always be bigger than this thing. All right, one more example. First thing, let's just do a quick test for divergence, right? Limit n goes to infinity of 1/ln n plus 1. This will go to 0, so we can't show directly that it diverges. What we can do is, this one is an alternating series, right? It's going to be plug in -1/ln 2 plus 1/ln 3 minus 1/ln 4, right? And it's going to switch back and forth. And it is an alternating series, and we could show that, we already showed that the nth term goes to infinity, sorry, the nth term goes to 0, and we could show that the next term, natural log of n plus 1 is less than or equal to 1/ln n plus 1. Again, that's the same idea. You're dividing by something a little bit bigger than this. So that's true. So this series converges. But what we want to note is, does it converge absolutely? So we want to check, does the absolute value of this thing also converge? So that's just basically 1/ln n plus 1. And does this converge? And there's no way to evaluate that directly. What you need to do is do a direct comparison test. and we're going to use we're going to compare it to the harmonic series, which is 1 over n, right? So we're going to compare it to 1 over n, and we need to show, like, if it's this one diverges, right? So what we need to show is that since this one diverges, we want to show that this one is greater than that one, and then since the smaller one diverges, so will the bigger one. All right, so let's just do some calculations on here so you can show that 1 over n will always be smaller than 1 over natural log n plus 1. So let's do some terms. 1 over n is, this is 1, 1/2, 1/3, so on and so forth, right? And then 1 over n natural log, we already did these up here, right? So it's 1 divided by natural log 2, 1 divided by natural log 1 divided by natural log 3, 1 divided by natural log 4, 1 divided by natural log 5. And you can see that except for that first term, right, that when I plugged in 1, the first term 1.44 was the only one that was actually bigger than this. So we can say for n greater than or equal to 2, 1 over ln n plus 1 is greater than, oh sorry, let's just make sure we can compare these two, like 1 there. So we're comparing 1.44 to 1, and we're comparing 0.9 to 1/2. So it's not for n greater than 2, it's for all n, right? Because even for 1 it was greater. But so we're comparing these numbers on the calculator with these numbers here, and what you can see is the natural log 1 is always greater than the 1 over n, and since 1 over n diverges and this one's bigger, right, it also diverges. So, you know, it's a little review of the direct comparison test. And so what we showed is that the original converges, the absolute value one diverges, which means that this is conditionally, converges conditionally. Or conditional convergence, right? Okay, hopefully this is kind of helpful. Your practice set is in the textbook again. These problems here. Please ask lots of questions and, you know, talk to each other, help each other out as you work on these things.